Hi, welcome to General Chemistry. I'm Jim Burnham. Today we're talking about matter and change. So let's look at the properties of matter. Well, what is matter? It's usually defined as something that occupies space, possesses mass, and can be felt by any of our senses. So milk and balloons and books and pens and chairs and you and this computer are all examples of matter. It's any substance that, as I say, occupies space and has mass. It's usually made of atoms and molecules, has various forms, as we're going to see, solids, liquids, gases, plasma, has properties like mass and volume and density. So that's going to be our working definition, anything that has mass and takes up space. It can undergo certain changes, and we'll talk about the changes that will track: freezing and melting, condensing and vaporizing, sublimating and reverse sublimation. So everything material is made out of matter. Sugar is one kind of matter. It's 100% sucrose. So matter that has a uniform and definite composition we call a substance. So substances, which are also known as pure substances, contain only one particular kind of matter. And as we're going to see, that's either going to be a pure element or a pure compound. So we can talk about physical properties of something. We can also talk about chemical properties of something. So first we're going to examine physical properties. And again, a physical property is something that can be observed without changing the composition of whatever we're looking at. So as we said before, something like density or color or odor or taste. You can observe the color of something, it doesn't change it. You can take the density of something, it doesn't necessarily change it. The melting point, the boiling point, those things don't change what the thing is. So here are some common physical properties of ordinary substances. So neon is a substance. Its formula is Ne. It's an element. It exists as a gas at room temperature. It's colorless. It melts at this temperature. It boils at this temperature. So anyway, these are the physical properties, and here are the chemical formulas that we might use to represent those. Here's sucrose that we just mentioned before, C12, H22O11. So now let's look at states of matter. There are three common states of matter. There's a solid, a liquid, and a gas. And under extreme conditions, which we don't usually deal with in chemistry, something can be a plasma. But we're going to just restrict ourselves to solids, liquids, and gases. And we know that water comes in all three of these forms, right? Frozen water, ice, it's a solid. Liquid water, and then when we boil it or it evaporates, it becomes a gas. So let's look at solids just quickly. The particles in a solid are very, very closely packed together. They're touching. A liquid, the particles are also usually very close together, but they can slip and slide past each other. And the particles in a gas are very, very far apart. So this is how we might represent the particles of a solid, a liquid, and a gas. And this is somewhat misleading because gas particles are really, really far apart compared to solids and liquids where they're touching. So here are the important properties of solids. Solids have a definite, a fixed shape. So this pencil, right, it has a fixed shape, a cube of a dice, something has a fixed shape, has a fixed volume. If you heat it, it will have minimal expansion, and it's essentially incompressible. So if you put pressure on it, it will resist squashing together. All right, so how about liquids? Liquids have an indefinite shape. So unlike a solid, which keeps its shape, a liquid won't keep its shape. It assumes the shape of its container. But it still has a definite volume, fixed volume. So it's like a solid in that it has a fixed volume, but it's unlike a solid in that it has an unfixed shape. When you heat it, it will experience moderate expansion. And again, like a solid, most liquids are almost incompressible. So you can't push them together. That's the basis of hydraulics, like a hydraulic pump or a hydraulic jack. So here we are just showing that it doesn't matter the weight that you stack on these things, they will essentially resist being squished. Function today. All right, again, this is a representation of a liquid where the particles are able to slip and slide past each other. Let's look at gases. Gases, like liquids, have no fixed shape. They have no fixed volume. They have massive expansion on heating, unlike liquids and solids. And they are super compressible. So this is going to be very different, right, from liquid. No fixed shape, no fixed volume, massive expansion, virtually, they're very, very compressible. All right, so here are all those properties all stacked together here. You might take a second and pause and just take a look at this. And this will reinforce all the things we've been talking about the properties of the particles that make up solids, liquids, and gas. And this is particles of matter. So these are the three basic states that we encounter matter in. All right, so let's say you're a stuntman and you're leaping off a tall building. What do you want to land on, right? Do you want to land on a solid or a liquid or a gas? Right? We already remember that solids and liquids are incompressible. So we want to land on something like a gas, right? We want something that can compress and absorb the energy of us flying off the building. If we landed on a sandbag or a bag filled with water, that would not be very comfortable. The words gas and vapor are often used interchangeably, but they have a specific meaning. Something is a gas if it exists in a gaseous state at room temperature. Something that is currently a gas but that is normally a liquid or a solid at room temperature, that we would call a vapor. So water, for example, is usually a liquid at room temperature. So if it evaporates, we would call that water vapor. But oxygen, we wouldn't call that a vapor. At room temperature, oxygen is a gas. So remember, a gas is something that's a gas at room temperature. A vapor is something that isn't usually a gas at room temperature, but currently is. All right, now let's talk about the difference between physical changes and chemical changes. So if we change something, but we don't change its composition, what it is in itself, that's going to be a physical change. And we're going to contrast that to a chemical change. So think about water, right? Whether it's ice or a solid or liquid, with water, or if it's a gas, it's still H2O, right? It's still one oxygen bonded to two hydrogens in a molecule, and so it doesn't change what it is. Again, just review the states of matter. So if something goes from a solid to a liquid, like ice, right, we call that melting. If something goes from a liquid to a gas, we call that boiling. If something goes from a gas back to a liquid, we call that condensing. So, the cold glass on a hot summer day, you'll see beads of water start to collect on the outside of the glass. The water's not sweating through the glass, it's condensing from the vapor in the air. If something goes from a solid, like solid carbon dioxide, dry ice, immediately to a gas, we call that sublimation. You've probably seen that at Halloween parties. And if something does that in reverse, we call that reverse sublimation or deposition. So, for example, if ice forms on the wings of airplanes as they fly through the air, from the water vapor, deposits, goes from water vapor to ice. And that's jumping directly from a gas to a solid. You'll also see this in a freezer, right, where you have frost built up. That is vapor from the air, gas, water vapor that has been frozen onto the cold surfaces. I guess we missed one there, liquid to a solid, and that's called freezing. So those are the 6 processes that you're going to need to know. Melting, boiling, so melting and freezing, you should learn those. They're opposite processes. Boiling and condensing are opposite processes. Sublimation and reverse sublimation or deposition are opposite processes. Okay, so a physical change is the change of the physical state, which leaves the underlying substance the same. So still water, if it's ice or liquid or vapor. The energy levels might change, the physical appearance might change, but the underlying structure of what it is remains identical. Okay? So if I split a log, it's still a log. All right, so those are physical. Here's some examples of physical changes. Crushing a can, melting an ice cube, boiling water, mixing sand with water, breaking glass, dissolving sugar in water, shredding paper, chopping wood, mixing red and green marbles, or the subliming of dry ice. So this takes us to the idea of mixtures. Mixtures are when we swirl together, physically combine different substances. Most of the samples we find in nature are mixtures of matter. So here is a mixture. It's chicken soup, and you can see pretty clearly the different parts of the soup, right? You got the noodles and the chicken and the carrots and the broth, right? So often we can identify the parts of the mixture, but sometimes we can't. For example, air is a mixture of oxygen and nitrogen and carbon dioxide and a whole bunch of other gases, but it'd be very difficult to discern those different gas particles in air. So sometimes mixtures are easy to see the parts of, sometimes not. But a mixture we define as a physical blend of 2 or more substances. And one important characteristic of mixtures is that they can vary in their percent composition. So your salad might have more cucumbers than my salad. In fact, I guarantee it will. But my iced tea might have more sugar than your iced tea, and probably will. So compositions can vary. There's no like fixed amount, I guess within a certain range, of sugar or a fixed number of tomatoes on your salad or whatever. Now, mixtures come in 2 basic flavors. They are either homogeneous, like homogenized milk, which just means they are smooth or uniform throughout. So that's our definition of homogeneous, uniform in composition throughout a given sample. But the composition and properties can vary from one sample to another. So the amount of fat homogenized in milk will vary depending whether I get whole milk, right, or 2% milk, or fat-free milk. So that will vary. It will be smoothly and uniformly blended, but the percentage of fat to milk can vary. The percentage of salt dissolved in water can vary, right? Something can be slightly salty, to super salty. And that can be true of even different bodies of water. Giant bodies of water can have virtually no salt, or they can be like the Dead Sea, with a ton of salt. Homogeneous mixtures are so important in chemistry that we give them their own name, and that is called a solution. So here's some common types of solutions. A gas-gas solution would be like we were talking about, carbon dioxide and air, and nitrogen and oxygen in air. A liquid gas solution would be water vapor in air. Gas liquid would be something like carbon dioxide dissolved in water, which makes it fizzy water, soda water. A liquid solution would be like vinegar mixed with water. In fact, vinegar is usually a 5% solution of acetic acid in water. Another solid liquid solution would be something like sodium chloride, a salt. dissolved in water. We call that brine. A solid-solid solution would be something like copper mixed in sterling silver, and we call that an alloy. We'll talk about that later on. So common types of solutions. So another way to say that something is homogeneous is to say that it has a single phase, a single area of uniform composition. The other way we can find mixtures, besides homogeneous, are heterogeneous. And that is where they are not smoothly uniform throughout. They're chunky. So homogeneous is smooth composition, smooth texture, smooth mixing. And heterogeneous is where you see different chunks, different areas, different phases. So here you see in this milk, maybe it came from a natural dairy, hasn't been homogenized. You see that there's a layer of fat riding on top of the milk. So these are two areas of different concentration. So something that's heterogeneous will have separate, distinct areas with different composition and properties. Okay, so remember, and this is the last part of this, different composition, that's the same with homogeneous, but the heterogeneous has separate, distinct regions of uniformity, separate, distinct phases, whereas homogeneous will only have one phase, one area of uniformity. So here's some classic examples of heterogeneous things. This vegetable pizza where you've just got the cheese and the bread and the tomatoes and whatever that healthy stuff is, and olives, different textured nuts, different areas of composition. There's a burger, obviously heterogeneous, the bun, the cheese, the meat, I don't even know what healthy stuff is. Lettuce, salad, of course. Here, a chocolate chip cookie, right? You've got the uniform batter, but then you have another area of uniformity, the chips. So this is two different areas, of two different phases. This is obviously heterogeneous. I know. Cookies. So some more examples. Homogeneous would be something like coffee. Even if you had something dissolved in the coffee, as long as it was dissolved and uniform throughout, that would be homogeneous. So you could have sugar dissolved in there and creamer dissolved in there. But as long as it was well mixed, that would be a homogeneous mixture. Cereal here would be a heterogeneous mixture. Smooth peanut butter, homogeneous. Chunky peanut butter, heterogeneous. So are you team smooth or team chunky? I am definitely team smooth. All right, as we said before, any part of a system that has uniform composition, we call that a phase. And that means homogeneous mixtures have one phase, and heterogeneous mixtures have as many phases as there are different areas of composition. So let's talk about how we can separate these various mixtures. Remember, a mixture is a physical swirling together, a physical amalgamation of matter. And so if we can physically mix it, you can imagine we should be able to physically unmix it. So if we mix iron filings in with who knows what, some sand or something, because the filings are magnetic, we could use a magnet, for example, to extract and separate the filings from the sand. So we have lots of different ways of separating mixtures. Right? We just talked before, we can use a magnet to separate something magnetic from something non-magnetic. We could use a filter. What if we had sand mixed with water and we wanted to separate that? We could pour the mixture of sandy water through a filter, and the filter would catch the sand, the water would run through, and presumably we could dry the sand from the filter and we'd have them separated. Decant is to pour off the top, so if I wanted to pour the fat that was on top of that milk in that one picture, I could decant that. You just pour off the top of something. So if you've got a mixture of oil and water, right, where the oil is floating on the water, you could pour off, decant the oil. You could evaporate something. So imagine if you had something like brine, salt water. You wanted to separate the water and the salt that was dissolved. you could leave it to evaporate, the water would evaporate away, and you'd be left with the salt behind. Let's say you wanted to separate something like blood. Blood is a mixture of red blood cells and white blood cells and platelets and plasma. So you could take a centrifuge and spin it down, and it would separate based on the weights of the various profiles in the blood. It would separate that out in a centrifuge. You could use something called chromatography, which is a way we can separate mixtures of different colors, like different colors of ink. Distillation is a way of separating something that has been dissolved or is mixed with water. So if we want to, if we have a mixture of alcohol and water and we want to concentrate the alcohol, we can distill it and separate the water out and then collect the concentrated alcohol. We become moonshiners. All right, so the difference between a mixture and a compound, right? So we're talking about physical mixtures, and there's a difference between that and what I will call a chemical mixture or a compound. Mixtures are physically amalgamated and can be physically separated or separated by physical means. But compounds cannot be as easily separated because they have been chemically mixed or chemically bound together, chemically combined. Something like water, right? Water is an oxygen bound up to a hydrogen. And even if I freeze it or melt it or boil it, it stays water. So to break water down, I have to use a chemical means to break it down, something like electrolysis, where I pass electricity through the water and I break the water back down into hydrogen and oxygen. But that is a chemical process, not a physical process. Now let's talk about elements and compounds. So let's distinguish elements and compounds. As I said before, pure substances as things that are just one thing. We can divide those into two groups. If something is a pure substance, it's either an element, pure element, or a compound. So a pure element would be something like sulfur or carbon. And a compound would be something like water or carbon dioxide. So here's helium, contains only one kind of atom. Oxygen, it's a diatomic molecule, as we'll see. It contains two oxygens in every molecule. So those are elements. Well, and then water would be an example of a compound that contains two or more kinds. So an element only contains one kind of atom. Helium is helium atoms. Oxygen is made up of oxygen atoms. Water is made up of a combination, a compound of oxygen bonded together with two hydrogens. Elements cannot be separated into simpler substances by chemical means. So once we get down to an element, that's the basic building block of matter. And those are the ones we arrange in the periodic table. There's about 100 of them that make up all the other things in the universe. Everything in the universe, in the physical universe, is made up of either pure or compounded elements. And so an element is something that can't be separated, can't be made into anything simpler by chemical means. So I can take water and decompose it into hydrogen and oxygen. Once I get to hydrogen and oxygen, I can't separate that into something simpler, at least using chemistry. So, as I said, they're the fundamental building blocks for all the other substances. Two or more elements can combine, as we said before, to form compounds of elements. So water is a compound formed of oxygen and hydrogen. Sodium chloride is a compound formed of sodium and chlorine. Ammonia is a compound formed of a nitrogen and 4 hydrogens. So here's the difference again. Compound is a chemical mix, whereas a mixture here is a physical mix. So if we took sugar, for example, and we heated it, we would see that it would first melt, it would caramelize, and if we kept adding heat, it would then decompose into water and carbon. And so we would break sugar down into its simpler compounds. Compounds are often quite different from their component elements, right? I mean, water isn't sweet and carbon isn't sweet, but if you combine them, right? If you combine carbon and hydrogen and oxygen in the right ratio, it makes this super sweet compound. So a compound is often very different in properties from the elements that go into that compound. So here is the metal sodium. It is highly explosive in water, highly reactive in water. Here is chlorine gas, which is a poisonous gas. If you combine sodium metal and chlorine gas, you get this really wonderful thing that you sprinkle on all your eggs. You get salt. So a highly reactive metal, highly poisonous gas, combined to form this super delicious, nutritious seasoning that you put on your food. So let's classify matter all the way through now. So we can have matter, and it can either be a pure substance or it can be a mixture of substances. If it's a pure substance, it's either an element, like helium or oxygen or hydrogen, or it's a compound, like water or sugar. All right, so here's some examples. Graphite is an element. Graphite in a pencil is pure carbon. But a compound would be water. Right, back to mixtures, right? We have smooth homogeneous mixtures or chunky heterogeneous mixtures. So lemonade would be an example of a homogeneous mixture where the water and the dye and the sugar are all a uniform composition. But if we have a mixture of oil and water, we're going to have different areas of composition, different phases of composition in a heterogeneous mixture. Okay, so again, and now we want to combine this with the idea of separation, right? So if we have matter that's a mixture, we can separate it, at least in theory, into its more pure substances, its elements and compounds, through physical means. So mixtures can be physically separated. But once we get to pure substances, we have to use chemical means to either make combinations. So if we make water out of oxygen and hydrogen, that is a chemical reaction. If we unmake water back into hydrogen and oxygen, then that is also a chemical reaction. So these are made and unmade by chemical means, just like these are made and unmade by physical means. Let's look at the symbols and formulas to express things chemically. As I mentioned, everything in the universe is made up of about one or more of the 100 elements that are found on the periodic table. Remember that elements can't be broken down into another substance by any chemical means. It's the simplest thing it can be without going into the subatomic level. Each element is composed of only one type of atom. We range these on the periodic table. So hydrogen has one proton. That's what makes it hydrogen. If you add another proton, it becomes helium. If you add yet another proton, it becomes lithium, and so on. In fact, all these elements are built up one proton at a time, which is also, and every proton is balanced by one electron. So one more proton, one more electron, you get the next element in the periodic table. Proton, one more electron, and so on. You can also have some neutrons thrown in there, but these are the building blocks of nature. These are the simplest kinds of substances that we can get when we break things down as far as we can with chemical means. This is what we get to. We get to the elements. So let's look at the symbols of some of these elements. As you'll see, normally the symbol is the first couple of letters, so here's Al is the symbol for aluminum, and Si is the symbol for silicon. Nitrogen, we just take the first letter, N. Carbon, C. O for oxygen. But we're going to see some that we are not what we kind of expect, because English is not the only language used in the periodic table. Some of them come from Latin, some from Greek, and some from other languages. So we're going to see some unexpected symbols for things like sodium. We'd expect sodium to be, I don't know, SO or something like that, SM, but it's Na. Why? Because it comes from the Latin natrium. What about potassium? Its symbol is K, not P like you'd expect. P is phosphorus, and that comes from kalium. Antimony is Sb for stibium. Copper is Cu for cuprum. Gold is Au for aurum, silver Ag for argentum, iron Fe for ferrum, lead Pb for plumum, mercury Hg for hydrogerum from the Greek, tin Sn, not Tn, right, like you'd expect from the Latin stannum, and tungsten is W from the German wolfram. So you should memorize these kind of weird ones, these unusual ones, because you're going to see them. Some of these are quite common, right? Sodium is very common. Iron is quite common, and copper. So you need to know these by sight, and you'll just have to remember, oh, these are not in English. These are probably Latin. And if you know Latin, great, but if you don't, still memorize these symbols. We use chemical symbols as a shorthand when we write out chemical compounds. Remember, that's when elements are bonded together. And compounds always have a fixed composition of atoms. That is, they always have the exact same definite amount of each element's atoms in that compound. So water, right, by definition is two hydrogens bonded to a single oxygen. And they're always going to be like that. Two hydrogen, one oxygen, that's water. That's its definite same composition, it's fixed composition. That's another way to illustrate a water molecule. So here are some common compounds: calcium carbonate, carbon dioxide, copper sulfate, glucose, hydrochloric acid, baking soda, sodium chloride, sodium hydroxide, water, and so on. So if you have calcium carbonate, it will always be one calcium to one, this is known as a carbonate, you'll learn that as a polyatomic. And these come in a 1-to-1 ratio. But carbon is going to be in a 1-to-2, right? This is a molecule. We'll learn the difference between a molecule and an ionic compound, but this is just telling us this is the fixed composition of these particular compounds. As mentioned before, all pure substances are either elements or compounds. And unlike elements, water will always have two hydrogens and one oxygen, right? Whereas a mixture can have varying composition. Okay? Your iced tea might be 1% sugar, my iced tea might be 5% sugar. So its composition can vary. All right, so again, this is kind of a choice chart. If we take a sample of matter, we can ask ourselves, can it be physically separated? If it can, it's a mixture. If it can't be physically separated, then it is a pure substance. And then we ask ourselves, well, can it be chemically disassociated, decomposed, turned into something simpler? Then it was a compound. Like we can take water, a pure substance, which is not a mixture, can't be physically separated, but it can be chemically decomposed back into its elements, hydrogen and water. If it can't, then it is a pure element. So, for example, if we took that sugar, we boil it up until we just get that black crust. That black crust is carbon. Can it be chemically decomposed any further? Nope. Therefore, it's the element carbon. Same way when we get mixtures. Okay, is the composition uniform? Does it have only a single phase? Is it smooth throughout? Then it's homogeneous. It's a homogeneous mixture. It's a solution of some kind. Or if the composition is not uniform, if it's chunky, then it's a heterogeneous mixture. We can actually subdivide these into colloids and suspensions, but we're not going to do that right now today. Let's talk about chemical reactions. In a chemical reaction, we're talking about something changing into something else. So the first thing we start with is called a reactant, and we're going to look at reactants changing into products. So here's an example of a chemical change, right? I take a log, a piece of wood, and I light it on fire, and it turns into some other things, one of which is smoke and water vapor and ash. Right? So I have changed it. I start with the log, and then through this chemical change, I get some products: water, smoke, ash, and so on. So a chemical change rearranges the atoms to form a new substance. And that's what chemistry is going to be focused on very, very largely. It's the new substances brought about by the rearrangement of the atoms. So we have a different composition than the thing we started with. So, right, Matt Damon in The Martian, right, he needs to make water to fertilize his potatoes, or hydrate his potatoes. And so he makes water because he's got hydrogen gas and he's got oxygen gas, and he knows his chemistry. He knows he can mix those two, and with a flame or a spark, he can transform oxygen and hydrogen into water. And it has a different composition from the original substances out of which it was formed. So let's go back to the idea of mixing, right? We can take iron filings and physically mix them with sulfur powder, and we get a mixture of iron filings and sulfur powder. But that's reversible. Right? We can reverse that, at least in theory. Anytime we can physically mix something, we should be able to unmix it. It is just a physical mixture. In this case, we could use a magnet to pull the iron from the sulfur. But if we mix iron and sulfur and then light it, it undergoes a chemical transformation, and we get a new compound known as iron sulfide. And that is irreversible. Okay, it's not going to go easily back to. We can do it in theory, but it usually is a process that is hard to reverse, and that hard to reverseness is a sign that we've undergone a chemical change. Remember, this was easy to reverse. This is hard to reverse. This is a physical change. This is a chemical change. And so here's what's going on. We're mixing the iron and the sulfur chemically to form a new ionic compound known as iron sulfide. So in a chemical change, here's the key: the reactants are converted to products. And we will often just set it up kind of like a math equation, right? We'll have, say, sodium plus chloride produces sodium chloride. The reactants produce the products. Okay, here we're going to take water, we're going to chemically decompose it, maybe through electrolysis, back into oxygen and hydrogen. And again, on that would be the reactant. So this would be the reverse of what Matt Damon was doing. He was running this reaction in the other direction, where these were the reactants and this was the product, but you can do it in either direction. So chemical changes are often accompanied by observable things like a color change or a change in energy. Something gets hotter or colder. So let's look at some examples of a chemical change. Cooking, right? You cook your eggs, you cook your bacon, you cook your toast. You're causing those things to undergo a chemical change. Okay? Burning wood, rusting metal. Those are things that we have a change of substance at the end of that. Remember, physical changes just change the arrangement, right? Breaking glass doesn't make it not glass, it just makes it harder to clean up, right? Mixing candy, shredding paper, folding paper, melting ice, chopping wood, cutting hair, boiling water, breaking eggs. Those are just physical changes. But if I burn the wood instead of chop it, if I rot the fruit instead of slice it, if I bake a cake, if I let the metal rust, if I do something with a battery, if I digest food, let milk sour, explode a firework, cook the egg, watch a flower undergo photosynthesis, those are chemical changes where one or more substances is forming a new substance. And so here are 5 common signs of a chemical reaction. If it releases light or heat, or produces a gas, or forms a precipitate, or we have a change of color. Now, is this the only thing? No, because you can have physical changes that are just temperature driven, right? Like when ice warms up, that's a temperature change, but that just is a change of physical state, not a change of substance. So again, these are not conclusive, but they're suggestive that a chemical reaction has occurred. There's signs or clues, right? So if bubbles are released, or the color is changed, or something starts to smell, or heat and light is released, or loud sounds are produced, those are signs that we may have a chemical reaction. Again, I brought the idea of reversible and irreversible. Most physical changes are reversible, right? I can freeze the water, I can thaw the water. I can boil the gas, I can condense the gas. So most physical changes, those 6 that we talked about before, are reversible. So here's some examples of reversible states of matter, right? Solid and a liquid, you can separate them with a filter. If you have a solid and a solid, maybe you can use a magnet or a sieve, right? So we can physically mix them, we can somehow physically unmix them. But a lot of chemical reactions, not all, but a lot of them are irreversible. So I burn the wood, it's hard to turn that back into wood. Ashes do not go back into wood. The metal rusts, hard to go back to pristine metal. Cook the egg, can't put it back in the yolk. It just can't go back to where it was before I cooked it. All right, one final topic is, in every physical or chemical change of matter, the mass of the matter is conserved. So this is known as the law of the conservation of mass. In every physical and chemical change, the mass is conserved. So if I start with 16 grams of methane and 64 grams of oxygen, right? I'm starting with 80 grams, and I have this reaction take place. I combust, I burn methane with oxygen, and I produce carbon dioxide and water. Well, what I'm going to get in my products is the same mass that I had in my reactants. They're going to be totally different, perhaps, because the methane has been turned into carbon dioxide and water and oxygen. So my reactants have changed, right? The substances that I used over here are different from the substances that I produce, but the overall mass had to be the same. Nothing was created or destroyed. So if I have, 1 carbon over here, I got to have 1 carbon over here. Or if I have 1 billion carbons here, and I have to do 1 billion, whatever. Whatever I start with, I have to end up with, even if I rearrange it. That's the law of conservation of mass. Applies to physical changes as well as chemical changes. So if I have 100 grams of ice and I melt it, I'll have 100 grams of water. Okay, nothing changes. Mass is the mass. So in all cases, the mass of the products must equal the mass of the reactants. All right, so to review the whole chapter, right? Matter is something that has mass and takes up space. The 3 common states of matter are a solid, liquid, or a gas. Pure substances are one thing only, and if it's a pure substance, it's either an element or it's a combination of elements known as a compound. A mixture is something that is physically swirled together, physically amalgamated, and therefore can be physically unseparated. Mixtures come in chunky, which we call heterogeneous, with multiple phases, or smooth, which we call homogeneous, with just a single phase. Oh yeah, here we go. So yeah, a quick review, right? Solids are rigid, so they have a fixed shape, a fixed volume, can't be squashed. Liquids have no fixed shape, but do have a fixed volume, can't be squashed. Gases have no fixed shape, no fixed volume, and can be easily compressed or squashed. So back to matter, as we just talked about the different kinds. Pure, either an element or compound. Mixture, homogeneous, heterogeneous. A compound, which is made up of two or more elements, chemically combined, can only be separated chemically. So compounds have to be separated chemically, whereas mixtures can be separated physically. We represent elements with symbols, some of which come from Latin, know the weird ones. Physical change is different from a chemical change. A physical change just changes the physical properties or the physical arrangement, like its location or something. Right? I can take a pencil and break it. That's a physical change. I take a pencil and burn it. That's a chemical change. So a chemical change changes the chemical properties. It changes it into a different substance. Reactants produce products. That's how we express chemical changes. I guess we could express physical changes that way too in many cases. And whether it's a chemical or physical change, the mass must be conserved. So you never create or destroy mass. Whatever you have in your reactants, you will have in your products, even if they're rearranged. All right, that's it. Thank you for your time.